and then data would be out.
Yeah. So let us now look at some key specifications of a cache subsystem. We'll come to better understanding of tag also in just a little while. As we discuss these key performance metrics, you will see the purpose of tag will automatically become clear to you. So we're talking about a memory, access time, capacity. There are two variables which you will very easily understand. Am I right? What is the capacity of your cache subsystem? That you can understand. Now, associativity. Associativity means that suppose I wanted to store latitudes of some locations, some addresses I wanted to store the latitudes and longitudes. How many latitudes can I store? And how many longitudes can I store? Or can I have can I also store, let us say, a photograph or something else of something in my system? So how many locations in the cache is a given address eligible to be placed in? For example, I have two buckets, latitude and longitude, and in bucket 1 I have 10 locations, in bucket 2 I have 10 locations. So associativity would be let us say 2 over here. So you will either come in the latitude, so any location in the latitude bucket or any location in the longitude bucket will tell you how many latitudes and longitudes you can save. Again, we will come to it in much more detail in just a little while. Replacement policy, I think this is intuitive. Suppose my cache is full. Cache is a very small memory. Suppose it goes full and I want to store or new data or run a new program, or आप movie देख रहे थे, उसका first sequence पूरा हो गया. Now the second sequence needs to be loaded. Which part of the cache would you replace? That is another key specification for the cache subsystem. We will look into it in detail as to what kind of replacement policies exist. Another feature or another specification around the cache subsystem is, do we have a unified cache or a separate instruction and data cache? In a unified cache, both data and instructions could be stored in the same cache. But as the second case suggests, you could also keep independent instruction and independent data cache. What could be the benefit of keeping independent instruction and data caches?
Sir, if you have independent instruction and data cache, then as we look at the normal execution of a particular instruction, first will be the fetch, the second decode, fetch, decode, execute, and the memory access, and finally the write, register write stage. So if we have unified memory, then the fetch stage and the memory read stage will coincide, and there can be a loss of single cycle, a cycle time. So if we have dedicated instruction and data cache, then we can then we can execute both of them independently, and there will be no loss of cycle time.
Yes. Also, it could happen that there is one instruction which is running on multiple data. If you have just one cache which is unified, it means every time instruction also needs to be fetched and every time data also needs to be fetched. But if you have separate caches, what does it mean? Oh, instruction, I have already put it out on my register. That instruction you can continue to use, but the data cache you may just access more frequently. So that also is one thing that would change. So overall power of the system, performance of the system can change depending on whether you are using unified or separate caches for instruction and data. So let's first look at access time. We're talking about 4 things here. The probability of a hit, that is probability of finding the address location that you want to access inside your L1 cache. Do you understand probability of a hit? See,
So मतलब हमें एड्रेस मिल गया.
yeah, the main memory is very huge. You only saved selective addresses inside your L1 cache or L2 cache and so on. So the probability that the address that you were looking for is now available in the L1 or L2 cache is P hit, probability hit. And then P miss, that it was not there. Now if it was there, then what happens? The memory, the small SRAM simply reads out the data and there is a fast access time there. However, if the hit doesn't happen, if there is a miss, then you know that you will have to go to a higher level of hierarchy, which means that the time involved would be higher, would be more. So there is a different timing now, which is called as T miss. So probability of hit into the time that it takes when you read after a hit, and probability of a miss and the time it takes to fetch the data from L2 cache or wherever, so that it is now available in L1 cache and for the processor, is referred to as T miss, the penalty linked to a miss. Okay, and therefore average access time is P hit into T hit plus P miss into T miss. Is this clear? Hello? Any questions?
So why we are writing it as average time? Shouldn't we write it as total time? Sorry.
Total time. Why? I accessed one memory location and it was a hit, and the time it took to access that particular location was just T hit.
Yes, sir.
है ना? So the total time is T hit only. अगर hit नहीं है, then I will have a different timing, which is T miss.
Yes, sir.
So how does this become total time? It still remains average time. There will be instances when there is a T miss, which is much longer.
अच्छा, overall देख रहे हैं हम तो इसलिए average.
Yeah.
Okay. Yes, sir.
है ना? So that is what is access time. Let's take an example. A memory, like a memory system, consists of a cache and the main memory. If it takes 1 cycle to complete a cache hit and 100 cycles to complete a cache miss, what is the memory average access time? Can you find this out? If the hit rate is say 97%, can you find this out?
So 3.97 units.
3.97 cycles. Is this clear?
Yes, sir.
Okay. Now, if you want less number of misses, you want the probability of hit to be higher, you can use a bigger cache. If you have a bigger cache, the probability of a miss reduces. If your cache could be as big as the main memory, there will be 0 misses. Are you with me?
So I'm not able to understand this statement.
So why is there a miss? Let us answer this question first. Why is there a miss? Why is something not available in the cache?
Yes, sir. अच्छा, हम ओवरऑल कैश की बात कर रहे हैं. मैं ये समझ रहा था अब तक कि वी आर चेकिंग ईच रो कि हाँ ये वाला रो में है या नहीं है, फिर ये वाले में है या नहीं है, फिर ये वाले में है या नहीं है.
हम कैश की बात कर रहे हैं.
हाँ, तो फिर कैश, if cache becomes equals to the main memory, then the probability of it will be 100.
Whatever you wanted is also available in your cache, is it not?
Yes, sir. Yes, yes, sir.
So there will be 0 PMS, everything will be hit.
Yes, sir.
That much you cannot do. DRAM is much denser cell than the SRAM. If you say that, okay, I will have the L1 cache as the same size as my DRAM there, then the area would simply blow up. Moreover, since the size becomes big, the performance gain that you had thought of earlier would no longer be there. Are you able to see this? Hello? Any questions? Clear है यहाँ तक?
Yes, sir.
Yes, sir.
Okay. So we say that bigger capacity could be better. However, bigger caches are slower. So there is a declining return on investment as the cache size goes up. When we talk of cache size, we also talk of what is called as cache line length, or also called as a block. So the concept of a line length is that if there is a miss and you need to fetch something from a higher level of memory, then do not bring in just one address. Bring in one full block. Why? Why is bringing a block more important than just one location?
So to exploit spatial locality. Yes, sir.
Yes, we just talked about it, that typically it will be adjacent addresses that would be, that would be required by the system. So you bring in a full block so that there are less number of misses. There is more number of hits. Additionally, when you do that, you will see that the overall access time, time to fetch reduces, because while the first access may take a lot of time, subsequent addresses could be faster. We call that as burst mode. So you get two kinds of benefits. First, the number of misses reduce. Second, that fetching a bigger address is overall cheaper in terms of total time than fetching just a small one word at a time. A bigger block will take lesser time in comparison to if all the words were accessed individually. Okay, and this function, are you able to see this? This says that I will bring about, let us say, 256 words in one block. But you want to bring that many words, but what happens? What happens is that the bus that you have from the memory to your processor is much smaller. It can at most transmit 2 words or 4 words. So whenever there is a miss, how many cycles would you need? First, you will need to access the word for the first time. Then, since there were only 4 words that could be accessed in one cycle, you will need what is called as 64 additional cycles to read the subsequent words. Are you able to see this? I say that my block size is 256, so that 256 consecutive words are written into my L2 cache or L1 cache, wherever. But 256 words may not be able to be transmitted right away. So there will be multiple transmissions required. And that is what we are representing by line length upon fetch width. And this is the delay taken when the subsequent address or subsequent location is being fetched. Questions?
So can I?
Yeah, Mohan.
Can I say that T first is T miss and T subsequent is T hit continuously?
No. So this is T fetch. This is T fetch is, you may say, T miss. Total T fetch is equal to T miss. अगर miss हुआ तो you will get 256 words from the L2 cache into the L1 cache. So that is what is T miss.
If I get this block from the L1 to block CPU, then
So CPU will use only one word at a time. CPU will give only one address.
okay.
The remaining you are copying simply to take benefit of spatiality. You said CPU has asked for only one word now, but I know that due to the spatial locality thing, I would anyways need to access the second, third, fourth word also pretty soon. So when I'm accessing a first word, let me get all the 4 words in one go. So T hit has not changed. P hit has not changed. So P hit would change because now you are bringing in the entire block together, and we're talking about what is called as spatial locality. So P hit will improve, but otherwise T hit has not changed. T miss or T fetch has increased a bit, in fact, because now you need to bring in more words.
Yes, sir.
So T miss बढ़ गया, P hit कम हो गया. P hit has reduced, P miss has reduced. P hit has improved, P miss has reduced, but T miss has increased. So how does this play out in terms of total delay? So, as you increase the line size, the total number of, suppose your L1 cache was 1024 words, let us say, and you said my line size is 256. So how many different programs related words, how many different programs can it cater to? 4.
Yes, sir.
So what happens if the numbers of programs increases? If the numbers of programs that I'm running in parallel increases, what would happen? There will be more misses. Now because I have no further location जहाँ पे मैं 5th program के लिए चीजें रखूं. So there will be misses now. So if my line size is very small, then I anyway have frequent misses because of spatial locality. However, if my line size becomes very large, even then there are misses. Are you able to understand this?
So line size was the number of words we can get at a time, right? So
Number of words you will fetch whenever there is a miss.
so like the block kind of thing we can get at a
Yes.
time, right?
Yes, line size is equal to block. As the block size increases, the total number of blocks that you can store in your cache reduces. Therefore, the miss rate starts to increase again.
So initially when I'm getting more blocks, then the hit will become less because we can get the data in that. But after that, that is not clear why it is increasing.
Suppose one
Because-
block. So each block refers to one particular program that you're running on your processor.
Okay. Okay.
Now you want to run 10 programs. You have only 4 blocks in your cache. The number of misses would increase, na? आप Word चला रहे थे. You're using Word on your computer, and you are using PowerPoint, and you are using Zoom, and you are using that streaming service. Now you say that I also want to use, let us say, I also want to listen to music while I'm on the call or whatever. So what happens? Now there is a 5th kind of addresses that you need, but so a 5th block that you need to store, but your L1 cache is already full with 4 blocks. Whenever you want to now access the music part, it will have to replace one of these blocks here. Replace means there was a miss and therefore replacement was necessitated. Is it clearer now?
So it is not like that ki my cache capacity decides what the line size would be. That is not the case.
So you will realize it does, because if it was a 1 kilobyte memory that was that smaller size, then I would have probably kept the line size at either 16 or 64. Whereas if it was a 256 kilobyte memory, I can keep it as small as 4 or as big as 256. Doesn't matter. For resource constrained chips, it may matter, and therefore, when there's a small cache, it could be of interest to see what is the optimal line size. Otherwise, यहाँ पे देखो, for most of the other capacities, higher capacities, line size has minimal impact. Look at this, 5% to 3%, the black line. The orange line, the bottommost orange line is something like 2 to 3% to almost 0%, almost 0.1. So the line size has to be decided in consonance with the memory capacity.
So who is deciding this line size basically? Like
you as a operating system designer.
Okay.
Or you as a firmware designer.
Okay.
Okay. So important thing to realize is the hit rate, the average time is an important parameter, performance indicator, than just the hit rate, because average access time includes the miss and the miss penalty in terms of timing. So while increasing line length improves hit rate, but it also increases fetch time. Is this clear? So the T-miss will increase as you increase the line size. But probability of hit would also increase. Probability of miss would reduce. It's a trade-off that you can always work out for your system. Okay? So this is another view that as the block size increases, the miss penalty increased. The miss rate initially fell, but then increased. And consequently, because the penalty was increasing, the miss penalty was increasing, and because miss rate was also increasing, the block size, the overall access time, average access time, becomes very sensitive to the block size. So in this particular example, for this could be an average block size that you may want to keep. Are you with me?
This we are plotting like for the 1 KB memory, right?
Whatever be the capacity.
So but in the earlier figure we were showing that when it was 256, it was not increasing.
So that was this particular experiment, na Raghav?
Okay.
This is not something that we have written in stone.
Okay.
This is one experiment just to demonstrate something to you. We ran 2 benchmarks and we could come up with this graph. You would run 24 benchmarks and you may see there is a, even this one, you will see that, okay, there are more misses and something like this could happen. I don't know. So it's about one benchmark we observed, but it is good enough to give you a feeling that this happens.
Okay, sir. Okay. That's a general relationship.
Yeah.
Sir,
yes.
Sir, when you explained the T-miss equation, so you said that it corresponds to one burst of transfer. Sir, so is the cache line length in any way related to the burst size?
So the fetch width, you could say, could be linked to the total number of words I can fetch quickly before selecting the next row.
Yes, sir. So the fetch width is the parallel transfer that it can
Fetch width
these
is the
many.
parallel transfer. Yes.
Yeah.
Okay. इसको थोड़ा सा मैं क्योंकि मैंने burst वाला word introduce कर दिया था. Let me explain it a little more. You know that a memory, let us say 8192 cross 32 memory that we are making in our project. In our course projects, we are making this memory.
Yes, sir.
So let us say this is the memory, but my processor is an 8-bit processor. So how many words are stored per, how many address locations would be stored per access? So I at any point of time, I am accessing 32 bits. In a way, for my processor, I am accessing 4 words. Are you able to see this?
Yes, sir.
So that becomes my fetch width.
Okay, sir.
Now, burst mode comes into picture where, because we add this concept of, let us say, mux 16. That is the exact instance we are making.
Yes, sir.
So what we are saying is that physically inside the memory, 16 words are placed right next to each other.
Yes, sir.
So when I access any particular row, I would say I will read all the 16 words in one go.
Okay.
16 L1 words, let us say L1 words कहते हैं इसको. नहीं तो वो इस वाले word से confusion होना शुरू. So this is processor words. Okay. So 1 L1 word is equal to 4 processor words. ये clear है?
Okay, sir.
But
Sir,
I also know that 16 L1 words are placed in the same row.
सर ये थोड़ा आप रिपीट कर सकते हैं सर, ये थोड़ा मिस हो रहा है सर.
16 L1 is happening in cache and the 4 words that is for the processor. So the main
Yes.
memory.
हाँ.
Okay.
नहीं मेन मेमोरी नहीं, मेन मेमोरी की बात नहीं है. Processor is an 8-bit processor.
Yes, sir.
So for a processor, one word is 8-bit
32
only.
bit. Yeah, it's 32 bit. So that's why 4 words.
Yeah. So one memory, L1 memory access can give you 4 words in one go.
Yes, sir.
Or one L2 access can give you 4 processor words in one go. Now what I'm saying is that there is also this concept of mux.
Yes.
What does mux mean? Mux means that physically when you access one particular row, 16 words will be selected. Out of them you will multiplex and select one word as an output.
Yes, sir.
है ना? So because 16 words were selected, I say that मैं उन 16 के 16 को read कर लेता हूँ और उनको एक जगह पे सेव कर लेता हूँ locally. ठीक है? तो अब जब मेरे को इन 16 वर्ड्स को एक्सेस करना है तो मेरे को बार बार मेमोरी के अंदर कंट्रोल ब्लॉक के थ्रू जाके वर्ड लाइन सिलेक्ट करके बिट लाइन डिस्चार्ज और सेंस एम्पलीफायर को एक्टिवेट करके कुछ करने की जरूरत नहीं है. डायरेक्टली इस लोकेशन से मैं 16 के 16 वर्ड्स फट रीड कर सकता हूँ.
Yes, sir.
So but
That is burst mode.
So but it will take like at least 16 cycles, right?
Yes. Yes, 16 cycles, but I can read.
Okay, so burst happens afterward, after this complete line of cache is available. So after that, we decide what the burst size can be. Like you've already saved the 16 words that we can now access very quickly.
Yeah. So why did we choose 16? Because we had mux 16.
Okay. So the mux
I could
size,
choose a burst length of 8 also or 4 also because my mux would allow that. But can I choose a burst length of 32?
No.
No.
So can you illustrate how mux 8, like burst size of 8 can be achieved?
Oh, I simply would say that, okay, मैं मेरे एक रो में, लेट अस से, आजा भाई एक मिनट, सो मेरे एक रो में 16 वर्ड्स थे, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16, लेट अस से 16 वर्ड्स थे, हाँ, but I say that I need 8 only, so I will read this, I will read this, I will read this, I will read this, and so on. So 8 हो गया implement.
Okay, sir.
Burst length of 8.
Yes, sir.
है ना? Smaller burst length तो implement करने में कोई challenge ही नहीं है, because आपकी line anyway 16 words को access कर सकती थी, अब आप कह रहे हो कि 8 को उनमें से आप use करोगे, which is fine.
Okay, so the cache line size is the maximum burst width we can have. Burst size.
No.
Because we cannot go beyond 16 words. So,
No.
right.
Burst length cannot go beyond 16. Line length की भी बात नहीं करी मैंने.
Okay,
So,
sir. Okay.
wait, let me come clear. So we are talking about different things. Line length, burst length, and what do you say? Word नहीं, इसको नहीं, ये नहीं कहते. Line length और burst length का difference आपको पता लग रहा है अभी? नहीं पता लग रहा, उसमें confuse हो रहे हो.
Line length is related to cache.
Cache subsystem,
Yes,
है
sir.
ना? Burst length is linked to your memory, independent of cache.
Yes, sir. And we can choose that. Burst length can be varied.
Burst
to an
length can be
extent.
varied, line length can be varied.
Okay.
You could say that my line length is 64 processor words. यहाँ पे कहा ना, line size is
Yes, sir.
64 processor words.
Yes, sir.
But in reality, one access would give you only 4 processor words.
Yes,
क्योंकि
sir.
आप 32 bit थे. So it means you will need 4 accesses to the memory
Yes, sir.
to get your 16 there.
Yes.
है ना? Now these 4 accesses could be burst mode accesses.
Okay.
So that T subsequent goes down. The only purpose is to reduce T subsequent.
Yes, sir. Okay.
समझ में आया?
Yes, sir. For the first time, it takes more time because we are fetching from the main memory, and then for the subsequent ones, it gets reduced.
Yeah, because
the line is
you
already
could be
there.
applying burst mode, you could be applying multiple things so that it reduces.
Okay, sir. Yes, sir.
ठीक
Got
है?
it.
So that is where we have these kind of curves in place then. That as you increase the size, the first penalty is higher, but subsequent words you can reach much faster.
So when we are talking of line, we are thinking in terms of blocks, but when talking of word burst, we are thinking in terms of the words of the proper memory that we were.
Yeah, of the SRAM.
Okay. And so each block can refer to like multiple rows.
Yes.
Yeah. Okay. Sure, sir.
ठीक है?